There we go. Today's little brief review. This is stuff you've done in the past, not hard stuff, but I want to go through it with you. Solving absolute value equations. Okay, so we'll start real easy here to kind of build up to what our approach is, and then we'll maybe try a few harder ones. So what about something like this? If I want to solve this equation, what's obviously the hard part? What looks awkward about this equation? What is it? The bars, the absolute value bars, right? So here's the first thing you got to remember, and this goes all the way through. We deal with this issue a lot in calculus too, for example. You can't really conveniently do algebra when you have absolute value bars in the equations or the inequalities. So what we always have to do is we have to make a conversion. We have to trade somehow the absolute value equation or later inequality for a compound equation or absolute or inequality. And a compound equation just means two equations. That's it. Okay, so we're going to trade this one for two regular, non-absolute value, easy equations. So what are they in this case? X equals 8 or x equals negative 8. And that makes sense, doesn't it? I mean, in this case, we can kind of reason through this just by knowing what the behavior of an absolute value function is. What's the job of an absolute value function? It's got one thing to do in life, and what is that? So we don't need to think about it in terms of distances or anything for now. But what does it do? If I input a positive number, does it have anything to do? No, it's still on the break. But if it does have a job to do if I input a negative value, then what does it do? It makes it positive. So that's its only purpose in life, right? It's to make the output positive. So then if the absolute value of x is equal to 8, what could have been inside the absolute value bars that's going to give us a value of positive 8 when all the dust settles? Well, it could have been positive, and it had nothing to do, but it also could have been negative, and the absolute value bars made it positive, right? So we know then that we're going to make the trade here. This single absolute value equation, we can convert into the two regular equations, either x equals 8 or x equals negative 8, and those are already solved in that case, aren't they? Okay, not a big deal. You got to take into account, what if the argument of the absolute value function, whatever was inside, was actually negative? The absolute value bars would have made it positive and given us an answer of 8, an output of 8. Okay, questions? Makes sense, right? Okay. Here's another way to look at that. And we'll get back to this later in the class. Do you remember graphing absolute value functions? A little bit in Algebra 1. They're always V-shaped. Remember seeing those? Maybe a little bit. It's all right. I mean, maybe you don't remember. An absolute value function, and we'll come back to this later in the class. We'll talk about how we do transformations of all kinds of functions, including absolute value functions. But for now, let's just reacquaint ourselves with what it looks like. What is the parent graph absolute value of x look like? Really simple. It's just a V where the vertex is at the origin and the slope of the right leg is positive 1 and the slope of the left leg is negative 1. That's it. So it's just a real simple V shape. Well, think about what this means. If we've got something like, I've got some absolute value function, like the absolute value of x, and I want to know when is the output of the function equal to 8. Okay, now if I think about the graph of a function, and this is good to have a conversation about this throughout the year. I input values into a function and the function outputs values, right? So if I write those as ordered pairs, which are the input values, the x's or the y's? What are the input values? The x values, yeah, right? So if I input a value of x equals 2, if I'm inputting 2 into the function, the way we would write that, I can say something like this. If my function is p of x equals the absolute value of x, then that's how I would say I specifically want to input an x value of 2, right? Say p of 2. Well, what's p of 2 equal to? It's equal to the absolute value of 2, which is what? What's the absolute value of positive 2? 2, okay? So that tells me then that I've got an ordered pair there. I input a 2, that's the x value, correct? And it output a 2 in this case, which is the y value. The output of a function is always the y value, the input would be the x value. And so then I should expect that on the graph of this function, that the function should go through the point 2, 2, which it does, right? That's a value of x and y that satisfy the equation. If I plug in 2 for x, I get back 2 for y, and so that's one of the infinite points that sits on that function, okay? Let's try another one. What if I input a value this time of -2? Well, my function, p of x equals the absolute value of x. So p of -2 equals the absolute value of -2, which is what? 2, okay? So then we would expect that if I write that as an ordered pair, I'm inputting a -2, and I'm outputting a +2. So I should also expect that my function goes through the point -2, 2, which it does. Agreed? Okay? So then if I ask the question something like, well, where does this absolute value function equal 8? Where is the output of the function equal to 8? Okay? On the graph, that would be way up at y equals 8, wouldn't it? So my graph doesn't go high enough. I'm going to make another one. So there's the y-axis, there's the x-axis, and here's my absolute value function. Everybody agree? Okay. If I'm solving the equation, where does the absolute value of x equal 8? I want to know where are the y values of the function equal to 8. Where's that going to be? Could be, there's going to be a place on the right side and a place on the left side. What can you tell me about those places? Say it again.
They're positive and negative sides.
Positive and negative sides. Can anybody tell me what the coordinates are going to be at those places? 8 and -8. We already did that one, didn't we? Right. We know that when we go over 8, we're going to be at a height of 8. If I go left 8, so go to -8, I'm also going to be at a y value of 8, right? Okay, what's significant about that? Well, I'm introducing you to a really good trick in algebra. This is a trick that we use with graphs. We'll be doing a lot of stuff with graphing technology. So we'll talk a lot more about this later, but here's your first introduction. So if I want to do something like I want to graphically solve the equation absolute value of x equals 8, well, I can think of it this way. I could graph the function y equals absolute value of x, which I did, right? That's graphed in purple. And I could graph the function y equals 8, and I could intersect those two functions, couldn't I? What does the graph y equals 8 look like? Horizontal line that intersects the y-axis at 8. We agree? So this would be the line. There's the line y equals 8. And the intersections of those two places would be what we already told you. At x equals 8 or x equals -8. So this isn't really high-level stuff, but I just want you to draw this connection. Now, can you make a connection between this graph and the answers we got? Right? Now this is, and we do this in math a lot. We'll switch into like algebra mode, where we're not really concerned about what graphs look like. We're applying rules of algebra, and you guys are very good at that, or you wouldn't be in an honors algebra 2 class. You're good at doing algebra, right? But it's important when we think about algebra that you kind of keep one foot in the realm of, well, what's the function doing? So I would encourage, like I talked about this in my calculus classes, you always want to be thinking in calculus about what does the function look like. If I were to graph that thing, what would it look like? Because that has a lot of bearing on how we approach the algebra, right? So same kind of thing here. Right here we just we solved this thing algebraically, but graphically it's equivalent to just saying, okay, well, where is the output of the function equal to 8? Well, where would the graph of the function intersect the horizontal line y equals 8? Okay, and you can apply this later on in math, and once again, I'm jumping way down the pike here. But how do you think we could go about graphically solving an equation like, or, yeah, an equation like this? What if I did something like, now I can do some stuff and solve that algebraically, but if I had graphing technology available, what's a way that I could solve this thing graphically? How can I use that same line of reasoning? Let's shift out of algebra mode here. Let's just think about this in terms of like functional mode. What do these functions look like? I want to know, when is the expression x squared plus 1 equal to the expression 3x? Right? I know we'd probably subtract 3x to the other side and try to factor or do something fancy like that, which we'll get to soon. But how could I do this if I could just input this into a graphing utility? How could I do this one? Ideas. Okay, well, what if I try the same trick? What if I graph the left side of the equation? Let's see what the expression y equals x squared plus 1 looks like, right? It's going to be some kind of a curve. It'll look like some, let me see the graph of that thing on the graphing utility. What about the right side? What am I graphing? Y equals 3x, right? Can anybody tell me what the shape of that curve is going to be? It's going to be a parabola, opening up or down, remember? Opening up, okay. So just roughly speaking, I'm going to get something like this. There's the graph of the left side of the equation, the purple graph. What about the right side? It's going to be a line, good. Slope of 3, y-intercept of 0. Okay. So that one's just going to look something like that, maybe, right? What do you notice? Do you see any intersections of those curves?
Yeah.
Yeah, there's 2 intersections. The intersections are occurring there and there, right? And if I had a graphing utility, I'll show you how easy it is with a graphing utility. So if I pull up Desmos, for example, I can write it as a function, or I can even just write y equals x squared plus 1. And let's see, can I make that? I bet I can. I can make it purple even. How's that? So it's purple. And then I've got the other function, y equals 3x. And let's make that orange. And there it is. And look what Desmos does. If I click on either one of those functions, it recognizes those are important points. Those are the points of intersection. And so if I click on those, I can see, yeah, I get 2 ordered pairs. So let's say that the question asked you to round the solutions to that equation to 2 decimal places. What would they be? Here, I'm going to take a picture. So here's my picture. Here's what we did. Now, how do I interpret that? You tell me. What am I going to do with that picture? What are the solutions? Where did x squared plus 1 equal 3x? Well, those are the points of intersection. I'm interested in the x values or the y values this time? The x values. My equation involves only x, doesn't it? Right? So my solutions would be, we get 2 of them. One of them is going to be x equals 0.38, rounded to two places, right? Or x equals 2.62. We agree? Pretty cool, right? That works. So that's just another way to think about solving equations. And we applied it with an absolute value function. We'll apply it later with other things. Okay, but now let's try to shift into, try to do this in a way where maybe we can shift into algebra, not rely on graphs, because you won't always have access to graphic technology. Like generally, the tests in here, you might want to know about this. The tests will be two parts. There's going to be a graphing utility part, sometimes, and there will almost always be a non-graphing utility part. So think of the non-graphing utility one as just straight algebra mode. The graphing utility one is you get to use technology to take shortcuts, and I encourage you to. Right? So you don't necessarily have to show a lot of algebra on those, on those kinds of problems. You're just trying to get an answer. Okay. What about this one? How could we maybe solve this equation? Same thing. What was our strategy last time we just solved an algebra equation? We set up two equations, right? The absolute value of x equals 8 corresponded to either x equals 8 or x equals negative 8. This is a little tougher. What do you think? What it is? This looks a little different. I just don't have an absolute value this time equal to a number. Got a bunch of other stuff in there, too.
So would you add 2 to 38?
Yes, you would. Good. Okay, so first step, let's maybe add 2 to those steps. So, and that's, and the reason we're doing that is we're gonna, you might remember this from previous years, but we have to isolate the absolute value stuff first. Because if we could get this down to something like the absolute value of negative 2x minus 6 equals some number, we'd be set, right? Because then we know that whatever's inside the absolute value bars either had to be that positive number or it had to be that negative number, and the absolute value made it positive, right? So the first part of solving an absolute value equation is we got to isolate the absolute value first before we do anything. And in order to do that, well, what's the first step? I would encourage you to not even look inside the absolute value yet, because there's nothing you can do there, right? It's really important to remember that you can't touch anything inside the absolute value function. You can't do algebra inside, right? So just think of it as being u or something. We'll just cover it up with a block. Don't even focus on it. But to get that by itself, what are the two steps in order to isolate the absolute value? Add 2, and then, good, and then divide by 4. So if we add 2, we get 40, divide by 4, we get 10. Okay, now that we've isolated the absolute value, what are the two possible values of the number that could be inside the absolute value bars? Negative 10 or positive 10, right? And that's where we make our split. Once we set this up to where we've got the, oh, pick it up tomorrow. There you go.